Hello, class. Sorry I couldn't be there today. The plan is this. We're going to spend about 10 minutes here, watch this video, and learn something new, hopefully. And during today's class, you should take your page 6 homework, check that. I got an answer key on Canvas for you. It's important. Thursday's quiz, there'll be some questions like what you see on page 6, also like what you see on page 7 and 10 and 11. You should take out your yellow packet, follow along with this video, take some notes on page 9, and then once the video is done, notes are done, you have the rest of the time today to work on pages 7. Skip page 8, there is no page 9, so page 7, page 10, page 11, and the first part of page 12. Don't worry about the last 3 questions on page 12 since we're not there yet. So I want to talk about ionization energy first. That was the basis of Chem Quest 5C. So 2 questions here. Which one has lower ionization energy? Now, you gotta figure out what does that question asking for. It's asking you to figure out which one would be easier to steal an electron from, right? Lower ionization energy means it takes less energy to take an electron away from an atom. So the question is saying which one of these two would be easier to steal from. So let's look at the first pair. All right, so there's a definition for ionization energy. At any point, you can pause it, read what's on the screen, or go back and re-listen to what I'm saying. And if you have any questions, either Wednesday, tomorrow, or Thursday, you can ask clarifying questions. All right, so if the ionization energy is lower, it will take less energy to remove to steal an electron. So the first two that we're comparing, I circled here. I don't have my tablet at home, so I'm using my mouse. So if I have to write something, my apologies, it's not going to be very good. So beryllium and nitrogen both are in the same period, period 2, and so they both have 2 shells, 2 rings of electrons. And Be, remember ENC, the pull from the nucleus, we can label going across the periodic table. And Be has a +2 ENC, and nitrogen is going to pull on those valence electrons that are higher, stronger, +5 ENC. So that's about 2.5 times greater than 2. So because nitrogen has a stronger ENC, it's going to be able to pull those electrons in tighter. So beryllium's pulling in those valence electrons +2 charge, nitrogen +5 charge. So bigger charge, bigger attraction, going to attract those electrons, pull them closer, and that's going to make nitrogen smaller. All right, so when it comes to stealing electrons, it's going to be easier to steal one from beryllium because those electrons are going to be a little bit farther away, and the +2 ENC, that's an easier force to overcome to steal that electron. The second question was comparing fluorine to iodine. They're both in the same family. So fluorine to iodine. Both have 7 valence electrons. Both have a 7 plus ENC. But look, iodine's valence electrons are way out here in the 5th energy level. Fluorine's valence electrons are here in the 2nd energy level. So because iodine's valence electrons are farther away, it's going to make them easier to steal, take less energy. So iodine is the answer for the second question. All right, so you might see a question like this. Compare the size of, hey, this, this, and this. So sodium +1, neon neutral, fluorine -1. So we have 3 different elements. One has a positive charge, one has a negative charge, and one is neutral. So how in the world could you answer this question? There has to be something common about them, something that you can use for a basis of comparison. And so here is where they're found on the periodic table. So you have fluorine, -1, neon, and then sodium +1. So when I have a question like this, I can make a little T-chart, double T-chart, and compare the proton number to the electron number. All right, so this is where I'm going to write in 9. So fluorine has 9 protons. Neon, element 10, has 10 protons. Sorry, once again, I'm doing this with my mouse. And sodium has 11 protons. So they have different numbers of protons, but fluorine, which should have 9 electrons, has a -1 charge. That means that this fluorine ion has 10 electrons. Neon, neutral, means it has the same number of electrons as protons, so it has 10. And then sodium, which normally has 11 electrons, lost 1, and that's why it has a +1 charge. So it has 10 electrons. So they all have 10 electrons. So which one is going to be the smallest? Well, look at the number of protons. Sodium has the greatest number of protons, so it has 11 positive charges pulling in on those 10 electrons, the best. And so sodium is going to pull those 10 electrons closer, tighter, making it the smallest. So sodium's the smallest. Fluorine, -1, only has 9 positive protons pulling in those electrons, so therefore it's going to have the hardest time doing so, and so those electrons are going to be able to stay farther away, making this atom the largest. All right, so sodium ion is the smallest, and the fluorine ion is the largest, and neon's right in the middle. So that's the way you tackle these types of problems. They all have the same number of electrons, so the more protons pulling in those electrons, the closer those electrons will be pulled, and the smaller the atom is going to be. All right, so we took a notes yesterday on ionization energy, so that should already be in your notes. If you still need that, then just pause the screen and you can finish up page 8. Here's a visual, help you see main group elements, group 1 and 2, and then groups 13 through 18. You can see their ionization energies. So this is the quantitative value for how much energy it takes to steal that first electron. And you can see as we go up and to the right, the numbers are getting bigger. So as you go across, generally speaking, the numbers get bigger. There's exceptions to the rule, but for generally speaking, it gets harder to steal due to the bigger ENC from the nucleus. And then as you go up, right, as you go up a family, the atoms get smaller, and it's harder to steal electrons from smaller atoms because they're closer to the nucleus, and that makes them harder to pull away. All right, so successive ionization energies. This is how much energy it takes to steal an electron, additional electrons beyond that first electron. So those numbers I just showed you on the previous slide, I'm sorry, I'm having a real hard time writing here. This is taking all my skill and focus. So these numbers I showed you here, this is how much energy it takes to steal that first electron, but some atoms can lose more than one electron, and so second ionization energy is how much energy it takes to steal a second electron from the same atom. Third ionization energy would be how much energy it takes to steal a third electron from an atom, and fourth ionization energy would, just keep going on and on and on. So what we see here, number 2, ionization energies will increase for every electron removed. It gets harder, in other words, it gets harder to steal each additional electron. So the first electron is always the easiest electron to steal from an atom. If you want to try to steal a second electron, it's harder. A third electron is even harder than the second. And that's because there's fewer electrons on the outside, less repulsion. So as an atom loses an electron, it gets smaller. And so that means the remaining electrons are closer to the nucleus, which makes them even harder to steal. All right, so let's take a look at this to finish up here. This slide. So number 3, it says, how much energy does it take to steal one electron and a second electron from sodium? So if we go back and look at this chart, look here, we got the first 12 elements listed down the left-hand side. This 1, 2, 3, 4 along the top edge, that is which electron you're trying to steal. So this is how much energy it takes. And let's see if I can do my highlighter here. How much energy it takes to steal one electron. If you say how much energy does it take to steal a second electron, you look at this column. How much energy would it take to steal a third electron from an atom? You look at this column. So if you look at hydrogen, there is no number here for the second electron because hydrogen only has one electron. So how can you steal a second electron? How can you quantify that if it doesn't exist? You get the point. So we're looking down here. This is how much energy it takes to steal sodium's first electron. So if you compare that to all the other atoms listed here, that's the lowest out of all these, the first 12, and so it's really easy to steal the first electron from sodium, but look at this huge number for the second electron. So why is it so much harder? Why is it over 9 times harder to steal the second electron from sodium? So that's where these numbers come from. They come from that chart above. And so let's look at this. So the first electron that we want to steal from sodium comes from the outside. It comes from that third energy level, but once it's gone, once this electron is removed and it's stolen by another atom, there's no more electrons in the third energy level. Third energy level is gone, so that means the second energy level is now the valence shell. And so now, instead of being a +1 ENC, right, if we do the math, this outer electron is being pulled in with a +1 ENC. Once it's gone, now the second energy level is the outer level. And so now, if you want to calculate the ENC, pulling in those second energy level electrons, the second energy level no longer is the core, it's now the valence shell. And so the only 2 electrons that are blockers, shielders, are the ones in the first energy level. So we only have 2 core electrons. So only 2 of that 11 positive charge is getting blocked out. And so this electron, these second energy level electrons are being pulled in with a 9 times greater force, right? Like 1 plus versus 9 plus. So you can steal one electron from sodium really easy, but you can never steal a second electron from sodium. And so that is why sodium, when it's an ion, when it's happy and stable like a noble gas, it's always going to have a +1 charge. It will never have a +2 charge. It's never going to lose 2 electrons because it takes way too much energy to steal that second electron from it. And just want to drive home the point. So look at magnesium. Magnesium, it takes 737 units of energy to steal a first electron, 1,450 units to steal a second electron. To steal a third electron, it would take 7,731 units of energy. I'm pulling these numbers from right here. That means that it is 10 times harder to steal the third electron from magnesium compared to the first, and it's more than 5 times harder to steal the third electron compared to the second. So why is that true? Well, let's look at the Bohr model for magnesium. Look, why are the first two easier to steal? Because they're in the third energy level. If we did the math, the ENC, there's 12 protons in the nucleus. There's 10 inner electrons, 2 in the first, 8 in the second, so there's 10 core electrons. They're going to block out 10 of that positive charge from reaching those outer electrons. And so the ENC is going to be positive too. All right, so these electrons are being pulled in with a +2 force. So once these are gone, once they're removed, now if you want to steal that third electron, look, that third electron is coming from the second energy level. So if we do the math for the ENC here, there's still 12 protons in the nucleus. But now there's only, because the second energy level is now going to be the valence shell, there's only 2 inner electrons. There's only 2 electrons that are shielding the valence shell. And so look at this ENC, +10 ENC. That's one of the biggest ENCs that you will ever see. So why does magnesium have an unusually high third ionization energy? It's because that electron comes from an inner layer, right? You can't steal it. It's not possible. All right, so electronegativity, we're going to save that all for probably, we're going to do a lab tomorrow, so probably Thursday. We'll finish up the notes Thursday, Friday. So that's it. I'm going to log off here. Hope you all have a wonderful day. Remember, check your page 6 with the answer key. I'll put answers up to page 7 as well. Take those pages seriously because that is going to make up the bulk of what your quiz is going to be on Thursday. So have a great day. See you tomorrow.